Okay, so this is the preview video for lesson 4, and lesson 4 is sections 2.6 to 2.12 in the textbook, and the definitions terms that we need to appreciate at the end of lesson 4 are here. And the 4, actually there's 2 2's here, right? 1, 2, 2, 3, and 4. So there are 4 lesson objectives, and these last 4 of these 4 lesson objectives, I'm going to argue that we've sort of already touched on. I'm really going to focus in this video on objective number 1. And objective number 1 is apply element, inductive, resonance, and hybridization effects to determine the relative strength of acids. So what we're going to do is we're going to look at these 3 things: elements, hybridization, resonance, and induction, and how they affect acidity, or their effects on acidity. So the first one is induction, and the example, the classic example that I want to use is acetic acid, fluoroacetic acid, and chloroacetic acid. Okay? So we're always going to map the strength of an acid over to the stability of its conjugate base. So this is the conjugate base. Right, and there's a chloroacetic acid's conjugate base, which we'll call chloroacetate. Alright, and what we want to do is look at these structures. There's 2 ways we're going to solve this. Number 1, we're going to look at the structures and make some explanation based upon what we see. The other thing we're going to do is we're going to look up the pKa's. I forgot to say this chloro. We're going to look up the pKa's and their equivalent methods, and you'll be able to use pKa's on the quiz or exam. So you want to have that, but you also want to be able to explain this stuff because you'll be asked to. So, is this a good acid or not? Well, the answer is it's called acetic acid, so yes, it's an acid. We're going to call this the baseline because the only difference between these guys over here, this looks like acetic acid also, but it's got a fluoro group on it. What do you know about fluorine? Fluorine's the most electronegative group. So what do you have here? What's the only reason this is the only inhibition to this to going to its conjugate base is the fact it's got a negative on it, right? And so something that's going to suck those electrons away via induction is going to be good. Fluorine's electronegative. It pulls the electrons out through the through the sigma bonds via induction, and that makes this a better acid. This is better than acetic acid. Okay, how much better? Well, we'll evaluate that here in a little bit. But it's better. Now, which of these is better? Well, which one is more electronegative? Fluorine's more electronegative, right? So this is going to be better than acetic acid, but not as good as fluoroacetic acid, or alpha fluoroacetic acid. Okay. The final way we're going to look at this is we're going to look up the pKa's of these. So let's go to the Pka table. Acetic acid is right here. That's the structure I drew just a moment ago. That's 4.8. Okay, fluoroacetic acid is going to be stronger. It's right here, 2.7. You see that? 2.7. And chloroacetic acid is right next to it, 2.8. 2.8. Okay? So we know that this is the strongest acid of all of them because it has the lowest pKa. Let me say that again. This is the strongest acid because it has the lowest pKa. Explained that on a previous video. That's the next strongest acid, and that's the weakest of all 3 of these. So what kind of question type would you get on a quiz or exam? Rank these according to their acidity in increasing order, rank in decreasing order, something like that, and briefly explain the order that you've chosen. Okay, that's a classic question type. There's a few ways this could be asked, but that's one of them. Okay, so let's talk about resonance now. That was induction. Let's talk about resonance. Okay, here are two acids that look similar, right? If you're talking about a donation of a proton, right, these guys look similar so far, but what if I put something over here that makes it like that? This has 2 carbons on it, this has 2 carbons on it, right? What if I do that? Which of these is a better acid? Well, we're always going to determine how good an acid is by evaluating the stability of the conjugate base. Okay, and or we're going to look at the Pka table, right, to evaluate how good an acid is. It's like doing an open book test if we've got this. So I'll ask you to rank them, and I'll also ask you to explain. So this won't have the this table doesn't have the explanations on it, but it's got certainly a lot of reference points for you. So we know that the pKa of this is 4.8 because we just looked it up. What's the pKa of this? We look for that. I'm fast at this because I've done it so much. We look for that. It's right here. 16. Which of those is a stronger acid? Right, the one with the lower pKa. How do we know? Well, because we looked up the pKa's. If you were to ask to briefly explain why, you would say, well, this must have a more stable conjugate base, and that would not be a fully creditable answer. You'd have to explain why it was more stable. And in the right answer somewhere would be the word resonance. Right? Can you see these are both bonded to a carbon? Both of them bonded to a carbon. So it's not the electronegativity of the thing that's on it. In this case, the difference is that. I should have given you a chance to draw that out for me. Okay? That's a resonance structure. I will ask you, go ahead and draw the other resonance contributor here. Draw the other resonance contributor. I've given you the hint with those arrows. Okay? So that's the second reason that, that's the second effect that we're going to study in predicting acidity. We did induction, then we did resonance. Now let's look at elemental effects. Okay, and the classic ones that I want to look at are these. This is really confusing because this is by far more electronegative, right? By far more. This electronegativity is 4. This is probably about 2.5. I don't know. I don't have that in my head. This is far more electronegative. It's the most 1. So you'd think that this would be pulling the electrons off, making that proton more happy to go. Again, we're mapping this over to the stability of the conjugate base. Right? Really, when we're talking about how good of an acid this is, we're really talking about how stable is this conjugate base. So, which of these is more stable? Well, this guy's super electronegative, so you'd think that would be the case. He'd be fine with that minus on it. But he's also very tiny. He's tiny compared to this iodine. I don't know the radii of those. You should look those up. Look up those radii. The radii of fluoride, not the atomic radii, but the ionic radii, and iodide. Be interesting to see what those were. But this is huge compared to that guy. And if you have something huge and it's trying to distribute that negative charge over something huge, it's a lot easier to lose a negative charge over something the size of planet Earth than it is over a BB. Okay, I've exaggerated, of course, the disparity in their sizes. But alright, so elemental effect says that the pKa of this is minus 10. And the pKa of this is something like 3.2, maybe 4.2. Wow. Wow. This is a billion times stronger of an acid than that. Because this pKa is minus 10, that's 3.2. Big difference. Billions, literally billions, right? Because this is p scale. It's a log scale. Okay, so we've looked at induction, resonance, and element effects. The final thing we're going to look at is hybridization. Hybridization. This becomes important later in the semester. Real important later in the semester, but for now, we're going to look at the difference of acetylene. And this is not acetylene until I draw the other things in there, right? But an alkyne, an alkene, and an alkane. We look up the pKa's of those. Let me ask you to look those up. Pause the video. Pause it now and look up the pKa's of those. These exact compounds are not necessarily in your pKa table, but you find something on here that gives you a good estimate of these pKa's. Starting now. Okay, let's suppose you just pause that and you look these up. You found that the pKa of that is 25. This is 44. And this is greater than 60. What? Wow. Or 60. Look at the difference in those pKa's. It's epic, right? The difference is. All right. So why is that? Because of hybridization. This bond right here is made of a carbon sp, hydrogen s, overlap of those two orbitals. That molecular orbital is made up of the overlap of these two atomic orbitals. This molecular orbital is made up of, and I'm going to ask you to fill in the blank using this language over here. This molecular orbital is made up of what two atomic orbitals? This molecular orbital, which we call a bond, is made up of what two atomic orbitals? Okay, so that's objective number 1 for lesson 4. That's all I'm going to cover for lesson 4. The rest of lesson 4 is things we've already covered in other ways. Okay, given an acid or basic molecule, predict the effect of changing pH on the structure of the molecule, which we've done here. Identify Lewis acids and bases, which we did in a previous video. Identify electrophile and nucleophile in a reaction. You know what? We haven't done that. I'm going to add that here. An electrophile is something that has a partial positive on it, or positive, right? It's a nucleus that can be attacked by electrons. Boom. That's an electrophile. I sort of implied this was sp3. I sort of implied this was sp3 hybridized. They're not all electrophiles are not necessarily sp3 hybridized. And a nucleophile is something that has electrons that can attack something else. Boom. Okay? These two terms are not going away. I'm not giving them a whole lot of press time right now, but they're not going away. This is going to be really, if our overarching question for organic chemistry is what are the electrons going to do, if that's the question, then we're always going to be looking for a nucleophile, which is the attacker, and an electrophile, which is the target. We're always looking for these when we're answering this question. What are the electrons going to do? We need a nucleophile, an attacker, and we need an electrophile, a target. And that's what these are. So that's objective number 3. And objective number 4 is something we've been doing all along, using electron pushing arrows to drawing mechanisms. Okay, best wishes. Look forward to talking to you about this soon.